Kinematics and Vectors. Example 3. A particle has an initial velocity given here, so that's for t equals 0, and it has a velocity at t equals 20 seconds given here. Now we're given that the acceleration is constant during this time period, and we have to work out the acceleration vector. So this is a SUVAT problem using vectors. So we start off with our basic variables here. So we're not interested in the displacement. We've got initial velocity, velocity at 20 seconds, and we're after the acceleration. V is equal to u plus at, our vector SUVAT formula. We substitute our values in, and now we need to rearrange. We've got an I term on the left hand side, we have an I term on the right hand side. If I move this term to the other side, so minus 5.6i minus 2.4i, and we do something similar with the j terms. Now we've got this, and then divide by 20 throughout, and we have our acceleration vector. And this is a constant, this is a constant. You can see that the acceleration vector is a constant. It's not a function of time. None of these terms have t in them. A constant acceleration, hence the use of SUVAT formulae. Now the same problem done using column vectors will have the following working out. So this is just v equals u plus at, rearranging, simplifying, t is equal to 20, and then we can divide both of these by 20, or we can multiply by 1/20th, which does the same thing, and then this scalar quantity will multiply our vector here, so both the x and the y components are multiplied by 1/20th, and we get this. And these numbers here are exactly the same as what we have here. Example 4. A particle has this initial position vector, so this is referenced from the origin, and it has a constant velocity, so no acceleration. We want to work out the position vector r at any given time t. So we have the formula for the position vector r for any given time, and s, the displacement of the particle, is given by this formula. Yeah, we're using this one because we have constant velocity. So we replace the s with vt, and now we substitute in r0 and v into here, like so. Then group the I and j components together. So this is the position vector r for the particle at any given time. To find the position vector of the particle at 3 seconds, we just substitute in t equals 3. That's straightforward enough. We're doing that into our formula here, t, and we get r is equal to 10i meters. So on a sketch, the particle at 3 seconds would be here, and this is 10 meters away from the origin. There was no vertical component, there's no j component here for the position vector. Example 5. A particle is initially at rest, so when t equals 0, its initial velocity is 0. We're using column vector form, and we also know that the initial position of the particle is also at the origin. At t equals 5 seconds, we're given the velocity of the particle, and we're looking for its acceleration. Given that the acceleration is a constant, we can use SUVAT formulae in vector form. So we're not interested in displacement, initial velocity, velocity at 5 seconds, and we're after the acceleration. V equals u plus at in vector form. So v goes here, u was 0, we don't need to add those in here, we can leave those, and a times t is 5a, then we divide by 5, or multiply by 1/5, and we have our acceleration vector, and we can see these are constants, the x and y components are constants, the acceleration is a constant, hence the use of SUVAT formulae. Now to work out the magnitude of the acceleration, we use Pythagoras' theorem on these values in simple trigonometry. So we have a horizontal component of 0.6, a vertical component of 0.8, so the longest side of this right angle triangle, using Pythagoras' theorem, is 1, so the magnitude of the acceleration here is 1 meter per second squared. Now we need to work out the position vector of the particle at 5 seconds into its motion. So we're sticking with Subat. Now this is the formula for the position vector. So the position vector for any given time is equal to the initial position of the particle plus its displacement from that position. So we need S, the initial velocity, velocity after 5 seconds, we already know the acceleration, and t equals 5 seconds. And the Subat formula we're going to use in vector form is this, s equals ut plus half at squared, and we put this into here to get this formula, and we already know that r0 and u are both 0, so these terms can be cancelled out, and we're left with half at squared. The acceleration is here, time is there, we substitute those values in, like so, and then 5 squared times a half, just simplifying, and then 12.5 times 0.6, 12.5 times 0.8, and we have our position vector of the particle 5 seconds into its motion. For further practice, try these questions.